Hi everyone, and welcome back to 201X recitation. This segment we're going to do a problem where we have a composite bar under axial tension. So we'll put the problem up in that corner there, and let's start by drawing our own diagram. So we have a steel bar of length L that is attached to a wall over at this end. There's our wall. And there's copper core on the inside just in this one segment. So let's make that copper. Okay, so let's label some points here. Call the end of the bar D. We'll call this point C, and this is going to be B. So we have length LCD over here, and length LBC over here. Okay, so we also know that our bar has a circular cross-section with an outer radius R0 and an inner radius Ri. And we have two forces on this bar. So we have a concentrated force right in here, which we're going to call Fc. And then we have another concentrated force here, which we'll call Fd. OK, so let's write down everything that we know about this problem. So first we know some geometric parameters. So we have that LCD is equal to 1 meter. And LBC is equal to 2 meters. And we also know that R outer is equal to 3 centimeters, and R inner is equal to 1 centimeter. OK, so those are our geometry parameters. Then we also know something about the materials. So we know that the modulus of steel is 200 GPa. And the modulus of copper is 100 GPa. And then finally, we're told that Fc is equal to 400 kilonewtons, and Fd is equal to 1,000 kilonewtons. So our goal in this problem is to find the displacement field as a function of x along the entire bar, and then also to find the maximum stress and the position along x, and also in R on the cross-section where the stress is maximized. OK, so let's just write these down. So we want ux of x, and we want sigma max of x and R. OK, so before we get started, let's just think about how we're actually going to get to the point where we can compute ux of x. OK, so usually when we do these problems, the first thing we compute is the axial force, right? So let's start with that. So once we have our axial force, then we can get our axial strain, right? Because the axial strain is just equal to n of x over EA effective. And in this problem, we can't cheat and make EA effective a constant because we have two different materials in here, right? So we'll have to compute EA effective. But once we have that, we can also write down that our strain is just equal to the derivative of the displacement field. So dux of x dx. So from that, of course, we can just find our ux of x by integration, right? OK, and then from the strain, we can also, of course, find the maximum stress, because we also know that sigma is equal to epsilon axial times E. OK? Good. So basically, we're finished our problem now. All we have to do is start plugging some things in. So let me just erase this line here so we have a little bit more room. We'll write that down later. OK, so to find n of x, we just need to make two cuts in our bar, right? So let's start with this end of the bar. So I'm going to do section CD. So I'm going to make a cut right in the middle of CD. So I have my axial force coming out in this direction, which is the positive x direction, which reminds me I didn't label that on my drawing. Let's put that back up here. So this is going to be our x-axis. OK, and then we only have force Fd coming from the end of the bar. OK, and then when we're finding our axial force doesn't care about the composition of the bar, so we don't need to worry about the core and the sleeve. OK, so we just write down our equilibrium. sum of the forces in x is equal to 0. So then we have minus Fd plus n of x. Right, so that's nice and easy. We have that n of x is equal to Fd. And let's just note down that this is in section CD. Okay, so now let's do our second cut. We're going to cut in the middle here. And we could cut from either end, right? We could keep this end or this end, but we don't know what our reaction force is, and this time we don't really care what it is, so we don't want to compute that. So let's include this end of the bar again, and we'll make our cut in here. So now we have FC at this point, and we have FD at the end of the bar again. And again, here's our internal resultant. Okay, so now let's do our equilibrium again. Sum over Fx equals 0 equals minus Fd minus Fc plus n of x. Minus Fd minus Fc plus n of x. And so then we get that n of x is equal to Fd plus Fc in section BC. Okay, so there's our internal resultant. So now, before we move on, let's just simplify our problem a little bit. I forgot to do this earlier, but I'm going to define some new variables up here so we don't have to carry around all these LCDs and LBCs. So we're just going to call this L star, so that this is equal to 2L star. Okay, and let's do the same here. So we have, let's see, we'll call this one E star, so that E steel is equal to 2E star. Okay, and then we can do the same with our R's, so that we get, let's just write this as area. We get that our area of the copper is equal to A star. And let's see, so we have area of steel, which is going to be different in BC. So in BC, it's just equal to 9A star, since the radius is 3 times the inner radius, right? And then, of course, the area of the steel in CD is basically going to be 9A star minus A star is 8A star, right? Okay, so I think we've redefined all the variables that we need. So let's go back to this, and the reason I remembered that is that let's just write this down in terms of x. So section CD goes from x is 0 to L star, and then section BC goes from L star to 3 times L star. Okay, great. So now we just need to find our EA effective before we can get to the strain, sorry. Okay, so remember that EA effective is a function of x. So let's do this again. We'll do it from x is equal to, or x goes from 0 to L star first. So we have E copper times A copper, which we know is A star, plus E steel times A steel, which we know is 9A star. Okay, and so we can also put in our new variables for the modulus, which I forgot to do. So we have, again, that E copper is E star. So here we just have E star, A star, plus 2E star times 9. Oops, that's not 9. Remember, that's 8, because we just want the area of the sleeve for the steel, right? So let's just make this an 8. Lovely. Okay, so we have 8A star over here. And so that gives us 17E E star, A star. Okay, so that's our EA in the section CD. And then in section BC, of course, we just have the steal, so it's really just E steal times A steal. So we can just write this down. Let's be thorough here. So we have L star goes from, or sorry, X goes from L star to 3L star. Then we have that our EA effective of X is equal to E steal, which is 2 E star, times the area of steal in this section, which is just 9 A star. And so this is just 18 E star, A star, right? OK, so now we have everything we need to calculate the strain. So let's just erase this stuff, and then we'll get to that part. OK, so we want to hold on to our strain. So let's write it down over here. So we have EA axial of X is equal to, and remember, it's just N of X over EA effective, which we just calculated. So we have FD over 17 E star A star in the region from X equals 0 to L star, right? And then we have FD plus FC over 18 E star A star from L star to 3L star. OK, so now we have our E of X, which is also equal to dux dx. So we can go right ahead and find our displacement field. So again, let's say in section CD, so from X is 0 to L star, we have that ux of X is equal to ux of 0 plus integral from 0 to X of EA of X. So FD over 17 E star A star dx, right? And then we have that for section BC, we have X from L star to 3L star. OK, so in section BC, we have ux of X is equal to ux of L star, right? Remember, we can't start from 0 now. So we have ux of L star plus the integral from L star to X of this guy over here, so FD plus FC over 18 E star A star dx. OK, so we don't know what the displacement field is at 0 yet, but let's just write this down. We can do this integral. That's easy because everything is constant, right? So we just end up with ux of 0 plus FD over 17 E star A star times X. OK, and here what we're going to do is we can say, let's write this as ux of 0 plus this component, whatever the value of the displacement field is at section C. OK, so let's just write this down. Ux of 0 plus FD. And here at segment C, we have X is equal to L star, right? So we can write down L star over 17 E star A star plus, finally, this integral. So we have FD plus FC over 18 E star A star times X minus L star. OK, so now before we can go any further, we need to find out what our ux of 0 is. So we need to apply some boundary conditions, right? OK, so our boundary condition is, of course, that at the wall, our displacement is 0, right? So at the wall, we have that we have ux of X equals 3L star. right? So we can plug in over here. So we have that ux, yes, so ux at 3L star is equal to 0. It's our boundary condition, which then equals, well, let's put in this part of the equation, right? So it's equal to ux of 0 plus fd L star over 17 E star A star plus FD plus FC over 18 E star A star times 3L star minus L star, which is just 2L star. Okay, and so now we can just solve this equation for ux of 0, right? Okay, and so then we just end up with ux of 0 equals minus this term. All right, so we have minus fd times L star, oops, over 17 E star A star. And then minus fd plus fc over 9 E star A star times L star. Okay, so let's just leave that in that form for now, and we'll keep it over here. And then let's finally write down our final expression for ux of x. Okay, so here's our final expression. We have that ux of x is equal to, we have fd over 17 E star A star times x minus L star minus fd plus fc over 9 E star A star. So we have this times L star. And so that's our expression for section CD. So x is 0 to L star. Okay, and then in CB we have fd plus fc over 18 E star A star. So times x minus 3L star. And so this is for L star less than x less than 3L star. Okay, so now we've finally answered part 1 of that question. But don't despair, part 2 is a lot simpler, okay? So we have our displacement field, but let's just go back to the strain, and from the strain we can compute the stress. So let's erase all this first. Okay, so now let's do the final part of the problem. We just want to find the maximum stress in the steel. So we can write that our stress in the steel is equal to Young's modulus in the steel times epsilon of x. So let's put our little x in there. Okay, which we know in our new notation is just 2 E star times epsilon A of x. Okay, so let's just compute the stress of the steel in section CD and in section BC. Okay, so sigma steel in section CD is just equal to 2 E star times our epsilon A over there, which is just FD over 17 E star A star. So our E's cancel out, and we get 2FD over 17 A star. Okay, and so that makes sense, right? Because we have force over area, which is always stress. So our units will work out. That's good. So then we also have sigma steel in BC is equal to, again, we have 2 E star times FD plus FC over 18 E star A star. Okay, which gives us FD plus FC over 9A star. Okay, so let's just plug in the numbers and compute this. So we have 2 times FD. So our FD is 1,000 kilonewtons. So 1,000 times 10 to the 3 newtons divided by 17 times A star is, oops, we never figured out what A star is. So A star is equal to a copper, which is pi times the inner radius, because that's the radius of the copper, right? So pi times 1 centimeter squared, which is 100 millimeters squared. Okay, so let's put that in. So times pi times 100 millimeters squared. Okay, and this one, we then have FD plus FC is 1,400. So we have 1,400 times 10 to the 3 newtons divided by 18 pi times 100 millimeters squared. Okay, so now let's make another substitution. We can just say that FD is equal to 2.5 times FC. And so then we get in CD, we have 5 FC over 17 A star. And in BC, we have 3.5 FC over 9 A star. Okay, so 5 over 17 is going to be less than 3.5 over 9. So the stress is going to be largest in BC. And we also know that the stress is going to be constant over the cross-section because the steel, well, because it's only steel in segment BC, right? So then we can just compute this, and we end up getting 495 MPa. Right? And so that's the maximum value of the stress, and it's going to be constant throughout the whole section BC, over the cross-section, and through X. Okay, we've finished the problem, so I'll see you next time. Thank you.